All right. Happy Tuesday, everyone. This is our the second week from the last. So we have 2 weeks to go, and we have two modules. Okay, but those two modules is relatively easier compared to our earlier modules. Those two modules is on our solid Earth geology. Okay, so we are going to learn the Earth's interior, the solid Earth, what's inside our Mother Earth, and also different types of rocks. And the last module, we are going to understand the internal processes, plate tectonics, volcanoes that can shape our land. So when we in the field, you see Santa Monica Mountains, you feel the energy from the inside because you understand that is the power from the heart of our Pachamama. Okay, but well, let me first give you an orientation on the very last two modules and what you are going to do. Okay, it's simple, but it's a little bit intense, but don't be scared. Okay, so here, let me share the screen. Here we go. Oh, okay, do you see my screen? Yes?
Yes.
Okay, wonderful. So let's go here. That is our class. Okay. All right. So the last two modules, number 9 and number 10. Okay. So here you can see it's a lot much simpler than the earlier modules. So we don't have other types of assignments, just quizzes. Okay. Because at the end of the semester, I know you have a lot of things to work on. Let's make it simple. You basically how to study it, how to finalize this semester with a big success. Number one, attend the next 3 meetings. Okay, I think that's the most efficient way to learn. And also go over the 2 lecture presentations. One is about geologic time, Earth interior, and rock cycle. That will be today and maybe part of Thursday. And also the next one, internal processes, plate tectonics, volcanoes, earthquakes. Okay, and that will be next Thursday and the following week, the Tuesday. Okay, so on next Thursday, I don't plan anything, just Q&A and maybe finalize some things. I don't expect, we, extend our lectures to Thursday, but just in case. Okay, and what you're going to do is your assignment is just 2 quizzes. Okay, so you attend the meeting, you go over the presentation, read the textbook, you're good to go. Okay, and in order to how to prepare those quizzes, go to your study guide. Okay, you have 2 study guide. Number one, this one is this module, and the next one. As long as you feel comfortable, confident about all the questions I posted there, you're good. Okay, you're ready for the quiz. Okay, so that is the things, the assignment, only 2 assignment for those 2 modules. Oh, by the way, I published another quiz last night for module number 8, ocean ecosystem. So once you finish your Q&A, the discussion about this module, and you comfortable about the questions I posted on the study guide, and you read your textbook, you're ready for this one. This one, the quiz a little bit long because you have 40 multiple choice, only multiple choice. Okay, that is all from your book. That's all from your book. But good news. I know it's many pieces of information, but you have 2 attempts. You have 2 attempts. If you're not sure about certain questions, you can try that again. Okay? And each time you have 90 minutes. Okay? So make sure you capture your little details online and on your textbook, and then can answer all my questions. Okay? So I see there's a question in the chat. Let me see. Okay, good. All right. Okay, so Any questions? So basically, in the next 2 weeks, you have 3 quizzes to finish. That's it. New assignment. I'm talking about new assignment. Okay. So this one is due December 13th. I think it's next Sunday, I think. And those two, that is the end of the semester. So that is Friday, I guess. I will be working on grading your climate change, the essay, the very last essay. Okay. So yeah, that's it. Any questions? Good. Okay, let's start our journey to explore the interior of our Mother Earth. Okay, so let's go to this presentation. Okay, so I also have my solo presentation from the previous semester actually to give you a recap of the the things I want to cover in this lecture. But today I will cover a lot of details. Okay, and these are your questions. Okay, so let's go to here. You can download it. Okay, let me present. So this lecture covered 2 chapters in your textbook, number 12, but only 2 sections, 12.2 and 3, okay? And then that one is about Earth's interior and rock types and rock cycles. That is in your chapter 14, 1 to 4, okay? So make sure you read it. It's a lot of fun, okay? At the end of the 14, they are talking about fracking. Trump talk a lot about fracking, to extract the gas from Mother Earth. There's a lot of debate on that. It's very interesting to read. Okay. All right, so let's start with geologic time. Okay. All right, so Mother Earth, she's very old from our perspective. But in the scale of universe, all the planets, she's in the middle age, okay? So 4.6 billion years old. Well, that is out of our imagination, actually. So as geologists and geographers, when we study the Earth's history, we need a ruler, okay? We need a ruler. Let me find my ruler. I have this little ruler, okay, if you can see, okay. On your ruler, actually you have different unit, right? Maybe this side is, centimeter and the other side is inch, okay? You have different measurement. And well, that is different unit, right? And if you pick one unit, okay, I see my centimeter, for example, okay, it divided by, a lot of the sticks, right? That is your millimeter subdivision, right? So here, as a geologist, as a geographers, we also, because this ruler is too long, we need to divide it into sections. And within each section, we want to subdivide into different subdivisions. Do you get my idea? That is where this eon, eras, periods, epoch, and many other subdivisions, okay, come in. Okay, so that is the idea. That is basically is a hierarchical structure of this 4.6 billion years history of our Mother Earth. Okay, so you can see the coarsest, the biggest division actually is called eons. And then within each eons, you have eras and period, and then period and epoch. Okay, so get this idea. This is the structure. You have a quiz question on this. Okay. All right, so, well, how you divide? Well, based on the geologic events, okay? For example, our eons, so you can see this is the eon, right? Let me annotate, change the color, okay? The very first one is eon, okay? This basically is too long. We break them into 4 parts, but it's continuous. Okay. So you can see here for eon, we just have how many? Can we count it? We just have 2, right? We have this Precambrian eon. We have this Phanerozoic eon, right? Okay, how do we divide it? You see this ruler, okay? Here, okay? Basically, in this, the first eon, we don't have any life, okay? The second one, we start seeing life here, okay? And here, within it, we have different era. So you can see, oh, how many years? We have this Paleozoic, okay? Paleozoic, you know, paleo means old, right? We also have this Mesozoic, okay? In the middle, we have this Phanerozoic, okay? In the middle, well, how we divide this Phanerozoic era? Okay, you start seeing life, okay, from here, from here, okay? Oh, sorry. This is Mesozoic, Paleozoic. Okay, you start seeing the very simple life from here, actually. The Paleozoic, that is the old life. Okay, and then Mesozoic, that is in the middle, and the Cenozoic is in the, you know, the very recent one. Okay, and then you subdivide it into period, into epoch. Okay, all right, so in the next slide, you can see, okay, based on different, here is the thing I'm looking for, okay? All right, so you can see from here, you start seeing the first vertebrate, right? The land animals from here, and then you have different dinosaurs, and dinosaur extinct, and you subdivide into another zoic, right? And you can see our human being actually is the very last second of this long history. So that is why this long history is out of our imagination. Okay, so how we divided the geologic and ecosystem, the events. Okay, all right. Okay, so that is, here is another picture to show you the divisions. Okay, all right. So the next question is, well, by the way, there's a video on the study guide. You can learn more. Okay, today I don't want to cover too much details, but you can find it, the video on that, to learn the entire history of what's going on in each period. Okay, and the next question is, how do we know? How do we know, for example, million years ago we have mammoth, right? We have dinosaurs. How do we know exactly the age, the year, how many years? We have the method. We call that dating. It's not the date. It's not the dating, you know, normally we are talking about, okay? That basically is we try to find out how old our rock is. Okay, we have 2 types of dating method. Number 1, we call that absolute dating. Okay, at the end of the day, through absolute dating, you will have exact number, okay, of how old the rock is. Okay, what we rely on? We rely on this radiometric decay in our rocks. Later you will see our rock is made of different minerals. Okay, and in the minerals, you have your molecules, you have your atom, and your atom, actually some atom is not stable. They're going to decay. Okay, so actually all the mineral, all the, you know, atoms, they're decayed. It just take different type of different, you know, different time. Okay, so some of them actually is very, very fast. Some of them very slow. Okay, but all the atom, they follow this rule. Okay, they follow this rule. We have, if you treat the first one, the entire, you know, they totally decay to a different, you know, atom. We call that child atom. Well, they follow this rule. The first time, okay, if you divide it, you know, here, follow this first half-life. What is half-life? As you can see in this diagram, let me annotate, where's my pen? Here. What does this half-life mean? That means at the beginning, you have 100% pure parent atom, okay? It takes this much time, for example, for this one, this is carbon 14, okay? 5,730 years for half of the carbon 14 become carbon 12. Okay, so you can see the, the blue or green sign bubbles and these orange bubbles, they're half and half. Okay, so 5,730 years. And then it takes another 5,730 years, another 5,730 years for those, the left parent to decay, half of them, okay? Second half-lives. So now at the end of the day, at the end of this stage, you have what? You have 25% from the beginning, parent atoms, the parent atoms left. And then you can see it takes another 5,730 years for those parents to decay. Okay, so they follow this rule. Why? Why we need to use this half-life? Because actually the absolute number of how many parents, how many children doesn't matter, only the percentage, guys. So it doesn't matter how large your rock is. You can have a smaller rock like this. You can have a huge boulder like our the half dome, right? It doesn't matter. It's the percentage matters. Okay, so that's very convenient. As a geologist, we can just take this sample. By the way, you're not supposed to do this. I'm not supposed to do this to take rocks from our parks, but I didn't know at that time. Just forgive me. Okay, I can carry it to my lab, and then I can analyze, the percentage of the parent and percentage of children, and then I know how old this rock is. Okay, does that make sense, guys? Yes? Yes, so percentage matters. So that actually enables us to do a lot of carbon dating you're probably familiar with, right? You go to the Natural History Museum, the dinosaur, how old she is, zoo in Chicago, right? And that is the absolute dating, okay? All right, so let me clear my drawings. All right, then this you can see is very, very time consuming. Okay, you need to go there to collect the rock samples, and you go to the lab, and then you analyze it, right? And sometimes we don't need that absolute age. For example, you go to, here's where, Grand Canyon, right? You just want to know, you don't want to know how old each layer is. You just want to know which one is first, which one is next. You just have this comparison. You have this sorting, right? For example, your mom and dad, your parent is older than you, right? You don't necessarily know how old they are exactly, right? So there's another dating method. We call that relative dating. We basically just want to sort the layers of our rock layers, okay? Which one is older, which one is younger, okay? So here is the laws or the principles we need to follow, okay? So the first one is, we call that, it's very long. It takes me some time to practice how to pronounce it. Now I manage it, and you can too. It's called uniformitarianism. Uniformitarianism, okay? So it assumes our Earth changes gradually, okay? The process has been operating in the Earth system. It's always there. To put it simple, let me use a metaphor. Like your grandmother or your grandmother, they make pizza, follow certain way, right? Certain family recipe. Okay, put water, flour, and that is a percentage, right? And you bake it at certain temperature. You have this family recipe from your grandmother. And then your grandmother do this in the same way. And your mom and you. Okay? And well, here. Now you see a pizza from your home oven. Okay? You don't have to know, right? You don't have to know how it was made because you know it's always made that like that. Okay? So that is this principle. Okay? The current tell you the past. So now you see in Hawaii, right? You see that black rocks, and we know that made of molten lava, right? When the lava chilled, like your butter solidified, they become this, dark rock, right? We know that. We see that now in Hawaii, and we know in many million years ago, Earth, Mother Earth, make dark rocks in the same way, like your grandmother make that pizza. Okay, so that is why when we go to Grand Canyon, when we look at the very bottom of those layers, okay, we know those rocks, they're made of lava. They're made of volcanoes, but we don't see volcanoes in Grand Canyon, right? Like you never see your grandmother, your ancestors, right? But we know she made pizza in the same way as you do, right? You do now in your house. Okay, so that is why this uniformitarianism is very important. Okay, understand our Earth. Okay, and in order to sort, why we say this one is the oldest, we have the second principle. Okay, we call that principle of superposition. Sounds very fancy, but it's really simple. The one at the bottom is the oldest one. The one on the top is the younger one. Because we assume those deposition that, that is layer upon layer, layer upon layer. Okay? We never, make our rock layers from top to the bottom. We always make that from the bottom to the top, right? It's operating on top of each other, just like you make cakes. Okay, so this is true, right? Okay, now we know the top one is the youngest one, and the bottom one is the oldest one. Okay, make sense, guys? Yes? Okay, all right, then here. What if, clear the drawings. What if your rock layers is not, horizontal in layers, just like your tiramisu, right? What if it's tilted? Actually, you see this a lot, if you drive along PCH, especially when you're very close to Ventura, you see this, right? It's just like a knife cuts through our rock layers, right? Okay, how you did that one? It's not on top of each other. You have another principle to follow. Let me go back. We call that principle of cross-cutting. Sounds very fancy too, but very simple. Why? Well, let me use a metaphor. When you have your tiramisu ready, you want to share with your friend, right? And you cut it. This is cross-cutting. Your cut is younger than your tiramisu, right? You need to have your tiramisu first, and then you have the rock, you have the cut next. Make sense? Okay, so remember this cross-cutting, we actually call that dike. It's always younger than the surrounding rocks. Okay, it doesn't matter, on the rocks, we just want to date this crust cutting. This crust cutting always the last. Okay, because you need to have your rock layer ready. Any questions?
I actually have a quick question.
Yes?
How does that happen, the cross cutting? Like, where does that section come from?
That is very, very good question. Okay. Like I said, million years ago in Arizona, Grand Canyon, we have volcanoes, right? Those volcanoes, they distinct, they are buried. But let's imagine, let's assume it's still active. One day, those lava, they regain the energy. They intrude into those rock layers. Does that sound similar to the next one? This one? Yes, exactly, right? So that is how it was made, okay? Because the Mother Earth sometimes is regain the energy again. This actually is one of the volcanic activity we are going to learn in module number 10. We call that intrusion. Good question, Maggie.
Thank you.
Okay, so here, okay. All right, so this called dike, D-Y-K-E, dike, or someone spell that D-I-K-E, same thing, okay? All right, let me cover the very last principle. It's covered, but it's called principle of inclusion, okay? This can help you in this situation. Let me clear my drawings. Well, Jane, here I don't have the cut. I have a core here. Right? Then which one is older? Which one is younger? Okay, so, well, here I show you. This intrusion is older. It's unlike our dike. This intrusion, this crust cutting intrusion is younger than the surrounding rock, but this one, this core, is older than the surrounding rock here. Okay, by the way, this is igneous rock, and outside this is volcanic ash, actually. Okay, so why you say that? Actually, it's also very simple, that principle, inclusion. Okay, let me use another metaphor. When we make burritos, okay, I know it's maybe close to lunch. Okay, you're hungry, burrito. Okay, so when you make burrito, you make the filling first, or you have the wrapper first. You probably prepare for your fillings first, right? Okay, then you have your filling first. Your fillings are those intrusions. So basically, that is, you have those pieces of rocks ready already, and then you have, for example, the lava pouring over this area with little pebbles. Okay, and then those lava solidified around those fillings, just like you wrap up your burrito. Okay, so that is why whenever or wherever you see those intrusions, okay, your intrusion, those cores, they're old rocks. Then they get wrapped up by the younger rocks. Does that make sense, guys? Yes? Okay, very good, very good. Okay, so in your quiz, you probably have a lot of pictures like this. I want you to be able to, figure out which one is older, which one is younger. All right, very good. Okay, then let's go to the next topic. It's a structure, the Earth's interior structure. Okay, so, well, maybe some of you still think our Earth is solid through. I won't blame you, because not long ago, actually 50 years ago, okay, people still think the Earth is solid through. We don't know. We have different layers inside our Pachamama. Actually, well, very good, very common question I always get is, how do you know we're in layers? We use earthquake waves, seismic waves. Here, let me go to the next slide first. Okay, we have earthquake waves. We have two types of waves. We have P wave and S wave, as you can see here, and S wave. Okay, so when you have an earthquake at certain location, those P wave and S wave, they also called body wave because they can penetrate through Mother Earth, the body, so body wave, but they behave differently. Okay, so you can see this P wave, those dark arrows, they can penetrate through both solid and liquid. So on the other side of the Earth, for example, right here, you can still detect it. Okay, earthquake happen here because P wave can penetrate through all the layers. You can still detect it. But S wave is special. Okay, S wave is those, gray arrows. They can only penetrate through solid, not liquid. So that is why we discovered 50 years ago, we have this liquid outer core. Okay, because on the other side, in the shadow of those, this liquid outer core, we cannot, people, geologists, they cannot detect the S waves because they disappeared. They get absorbed by those liquids. Okay, so that is why we discovered this liquid outer core. We know at that time our Earth is not solid. Okay, and how we differentiate those layers, as you can see, your P wave and your S wave, when they go through different layers, those boundaries, okay, between different layers, they change the direction and speed. Okay, so we can detect those smaller changes and we can draw the boundary. Okay, so that is why we know, oh, our Mother Earth, actually you have many layers. Okay, that is how we, define, we know the depths. Okay, so anyways, we basically have those 4 layers, but in this mantle and crust, you have sublayers. Okay, so we have solid inner core, which is here. Okay, we have liquid outer core. This one, S waves helps us. Okay, and then you have your mantle. Later we'll cover more about those sublayers. And then that is our Earth crust. Okay, all right, so we go this inner core and outer core. Basically, you just have different texture. We call that texture. One is solid, inner core, and the other one is liquid. Okay. Oh, by the way, let me go back. You can see this profile showing you the temperature, right? Okay. You can see this is the top, this go deep, the depths. Okay. So you can see our inner core actually is very hot. It's like more than 5,000 degrees Celsius. Oh my gosh, it's almost the temperature close to the sun surface. At the surface of the sun is 6,000 degrees Celsius. Okay, but this outer core, you can see, relatively cooler, right? Okay, about like 4,000, 4,500 or something like that. Okay, here's another question I always get. Jing, why? Inner core is so hot. Why is solid? Why those, materials, those iron and nickel, they don't melt. Okay, they don't melt. Why? But outer core is melt. Okay, here's another thing, guys. Along with this temperature, when you go inside of our Mother Earth, your pressure also increases. Okay, so the tremendous amount of pressure in the inner core actually can compress those materials together, don't melt. Melting is just like you change your ice cube into liquid water. Remember that molecular texture I showed you in the lecture, right? They're basically falling apart. But this pressure inside the Mother Earth in the inner core they're able to hold those atoms and molecules together, so don't melt. Okay, so that can increase the melting point of those materials. So that is why your inner core it's solid, but outer core, the pressure is not high enough. They fall apart. They become liquid. Make sense? Okay, so that is the pressure. Okay, you will read it in your book. Okay, just hope that makes sense to you. All right, so that is the difference. Okay, and you can read more details in your textbook and also the videos. Okay, and let's go to our mantle, the second, big layers. Mantle, actually, we can divide it into 3 sublayers. Okay, based on the texture as well. Okay, based on the texture, solid, liquid, this type of thing. Okay, but don't get me wrong, our mantle, they all solid. They just different types of solid. Okay, it sounds weird, but it's common sense. Like this rock is rock solid, right? Okay, you have something like my ruler. It's solid, but I can bend it, but it won't break, right? Okay, we call that plastic solid. Okay, you also have your chips, right? Your tortilla chips. That is crispy. All right, that is crispy solid, right? That is different texture, guys, for the 3 mantles, 3 mantle layers. Okay, so you can see the lower mantle, the very bottom one. Okay, this one. Let me highlight it. This one. We call that rigid mantle. That is this rock solid. Okay, you cannot change the shape. I cannot change the shape of my rocks. I respect it. But, well, why? Because the pressure. Okay, because the pressure. Because the pressure is so high. Okay, and here, and also the temperature is not high enough to melt it. Okay, and here in the middle, this one, okay, is this one, plastic mantle, or in many book and literature, we call that asthenosphere. Asthenosphere. Okay, well, literally it means weak layer, weak, W-E-A-K, weak, soft layer, plastic solid, like my ruler. Basically, you can change the shape. It's, squishy, like your cushion, like your couch. Okay, you can change the shape. So when on top of it, those materials, like you have a higher and higher mountains, like our Himalaya mountains, she's growing, those asthenosphere actually will be pressed down. Okay, like you have a indent in it. Okay, so we call that the asthenosphere, the rebound, okay, and depression. Okay, later you will see. Okay, so this is why this layer is plastic, because temperature is increasing, but pressure is not high enough to hold them together. But still, they're in a battle. Sometimes we call that partial melting. Okay, so it's just like you put your butter in your saucepan, but the heat is not high enough to totally melt it. It just softened it. Make sense? Okay, so basically pressure get less. Okay, and then you go to the top layer, lower mantle. Okay, lower mantle. Well, here temperature failed. Temperature lose the battle. Okay, because it's too cold to melt those materials. So you can see pressure is able to regain the place, the ground, and to hold those materials together. So on top of it, this lower mantle, okay, or we call that rigid upper mantle, becomes solid again, rigid again. Okay, rigid again, like your lower mantle. Okay, so you can see our mantle is really like a sandwich, like your Oreo cookie, right? You have a cookie layer here, you have a cookie layer here, and in between that is your softened cream. When you squish that, it can, like a mochi, right? You can press it. You can press it like your mochi, your sandwich, ice cream sandwich. Okay, I think that's a good metaphor to, help you memorize the texture of different layers. Okay, by the way, you don't need to, physically remember those steps, those numbers. Don't do that. No one can do that. Professor Jin cannot do that. Okay, well, the most important thing is the texture. Okay, which layer is soft, which layer is liquid, and which layer is rigid. Okay, make sense, guys? Okay, very good. Clear the drawings. All right. Okay, then go to the crust. Let me check. Okay, good. Go to the crust. Crust, we have two types. Okay, two types: oceanic and continental. Okay, they're not, who is on top of who, right? They're separate. Basically, well, don't get me wrong. You hear that oceanic, it doesn't mean it only contains ocean or it only contains land. Okay, we divided basically based on what? Based on this composition. Okay, based on this composition. So you can see we call that oceanic. Basically, that contains a lot magnesium and iron. Okay, those minerals, those molecules. Okay, and as a result of that, as a result of this composition, our oceanic crust, this flavor, this type is darker. Okay, it's darker compared to continental crust. This composition, we call that feldspar rich. Basically, you can tell a lot of granite. Okay, granite. So you can see my rock here, this one, I will say it's dark. Right? It's rich in iron and magnesium. Right? So I will say that probably come from oceanic crust. As opposed to I have a lighter color rock. Do I have that? I don't. I like ocean, so it's oceanic. But later you will see a granite. You will see a very light color. Okay? That actually is from our land. Okay, from our continental crust, light in color. Okay, and because of this composition, you also have different density. So you can see your oceanic crust, the density is higher. Okay, it's higher, and your continental crust, because this, iron rich, you have a lot of, calcium, those light minerals, that is very less dense. Okay, so this actually give you the foundation, theoretical foundation, when those two types of crust, when they meet, when they collide, the behaviors of those two crusts. Okay, so that is lead to the next module, plate tectonics. You probably heard that we have oceanic plate, we have continental plate, right? So when they collide, this heavier oceanic plate will plunge, because it's denser, it's heavier, will plunge beneath your continental crust because it's lighter. That creates a lot of very interesting, landforms like your, Mariana Trench. Okay, so that is the next module. Okay, any questions by far? All right, remember we differentiate those two based on composition, not what they contains, okay? Because later you will see some continental crust extend over the ocean, okay? All right. Oh, clear the drawings, go to the next. Okay, so this is the rebound I'm talking about. Okay, we call that isostatic rebound and subsidence. That's all because you have this very soft asthenosphere. Okay, so when you have mountain building, that is the, one process, your mountain get higher and higher. Okay, and this mole, by the way, is the boundary between your crust and your mantle. Okay, this is this boundary. Okay, this one will sink. Okay, will sink. Then we can identify the mountain growth, right? We have GPS, we have all different type of devices. We can measure very, very precisely the elevation change. So that is how we measure the height of our different mountains, for example, Himalayas. Okay. All right. Okay, I covered this. Let's go there. Okay. So today, let's see, I have 10 minutes left. Well, let's cover different rock types and then later we can continue. Okay. All right. Then first thing I want to be clear is our Earth's crust. Okay. All these rocks we found, 99.9% is from the crust. Okay, so that is why we first need to learn the composition, the chemical composition of our Earth's crust. Okay, we have different elements. Okay, chemical elements. Now we are talking about oxygen, silicon, aluminum, iron, calcium. Okay, all these type of things. Okay, so you can see the most abundant actually is oxygen. Okay, the second one is silicon. Okay, so you can see those two, you add them together, it's about like 80%, right? So most rock in our Earth's crust, they contain silicon and oxygen. That actually give us a big family of this mineral. We call that here, let's see, silicates. Okay, so this is the silicates, this big mineral family, we call that silicates. A very little amount, percentage, okay, composed of other mineral, other chemical atoms, we call that non-silicates. Basically, you don't have this silicon, this element. Okay, so you can see you don't have other things. Okay, but there are little amount like our trace gas, carbon dioxide in our atmosphere. They actually very, very valuable. Okay, for example, this highlight. What's that? That is the salt you and I rely on every day. Okay, you can eat your. I always tell my students, you can eat your rock. Some people don't believe me. Jin, you're crazy. You cannot eat rock. Actually, you eat rock every day. Your Himalayan salt, that big pink, crystal, the salt, that is a rock, right? You eat it every day. That is why these, geology actually is amazing. Okay, Jin like it. All right, okay, anyways, let's go back. When you have those minerals, okay, you are ready to assemble when you have those elements, okay, like oxygen, silicon, aluminum, and iron, those four top abundant minerals, elements, and then you combine them together, you will have your minerals. Okay, that is your mineral family. So that is, we are talking about feldspars, we're talking about quartz, olivine, amphibole, okay, biotite, okay, those type of things, okay? So how we define a mineral? What is a mineral? It's not a rock, by the way. It's not a rock, it's a mineral. Okay, so what is mineral? Mineral is naturally occurring, inorganic. It's not living things, okay? It should be solid. And the most important thing, you have this definite chemical composition. You have a defined, structure within it. So for example, like this one, silicates. right? These silicates. You know you have your silicon, you have the oxygen. If assemble those two elements in this way, like a pyramids, right? Okay, then combine with, you know, your calcium, you will have one type of mineral. Okay, but if you have different texture, like this one, okay, mica, okay, mica. If you assemble those, you know, different chemical elements in layers, okay, or this pyrite, okay, you will have different minerals. Okay, they have different, you know, chemical composition and also different structure. So that is also show up those text, those structure. They show up when you see those minerals. You can see those mica. They're in layers, right? As opposed to, let's see. Let me find another one. Another picture. Okay. Okay, like this quartz. Quartz, if you break it, they're like pyramids, right? Quartz basically is these pyramids, okay? This pyramid structure, okay? So that is why different minerals, they have different, you have all these type of, you know, characteristics of your minerals, okay? You have different composition, you have different, we call that cleavage or fracture. So when you break it, they break in different way. That because they have different structure, okay? And of course, they have different color. They have different, you know, strack. Basically, when you powder them, when you make them into, you know, mineral powder, they will show up in different color, okay? And different hardness, different luster. Okay, so that is all because they have different composition and structure. Okay. All right. Okay. Then you have your two big families, silicates and non-silicates. Okay, and then here, oh well, this is not your geology class. Okay, your Professor Collins or Professor Malanis, they will ask you to, you know, memorize all these type of subfamily. But in our class, you just need to know we have silicates, we have non-silicates, and you know what's the difference. Okay, all right. But in your textbook, you have a big chunk of you know, paragraph to show you all the valuable valuable characteristics or commercial use of those non-silicates, those minerals. Very interesting to read. Okay, so that is information in your text. Let's see. Okay. Let's see. All right, so let me cover the very last slide, and then on Thursday, we can pick up from here. Okay. All right. So classification of rocks. Then what is rock? Jing told you mineral is not rock. Then what is rock? Right? Okay. So let's go here. Okay. All right. Mineral and rocks. What's the relationship? Okay. Rocks is a solid mass composed of one or more types of minerals. Okay, so basically you have different minerals. You combine them together, boom, that is your rock. Okay, so for example, this is your granite. That is one type of rock you can find in your continental crust. When you see that, when you have this sample, you look at it with your, you know, naked eye. Actually, you don't need a microscope. You will see all different colors, right? Those different colors, they're different minerals. They're different minerals. Okay, so you can see this pink one is pink feldspar. We also have this white pale color feldspar. That's different, although slight different composition. Okay, you also have this translucent quartz. You also have those shiny, you know, mica. Okay, so our rock actually is assembled. Okay, you assemble all the different minerals, you have different rock. Okay, so basically, yes. Why rock is like this? That is, in our Mother Earth, you know, she is very, very hot inside, right? Have a warm heart. It can melt all the rocks and just you have liquid, like a bowl of mineral soup. Okay. And then those minerals, they can chill. They can solidify when the temperature gets, lower and lower. They can solidify, in different way. They can assemble different liquid minerals, and then you have different type of igneous rock. That give you igneous rock, guys. Okay, so igneous rock is basically forms by cooling and solidification of your liquid mineral soup. We call that magma. Like your lentil soup. Okay, you just chew it, and your carrots, your celery, your lentil will, combine together, become an igneous rock. Okay, but on Thursday you will see they, cool down in different way. You assemble different minerals. Okay, you will have different igneous rock. Okay, and from there, guys, from your igneous rock, when you break them down into pieces, and then you just like you break down your cracker, and then you make your, pumpkin pie, the crust, you press them. That is your sedimentary rock. Okay, but if you rebake it, you recook those igneous rock or sedimentary rock, you will change the characteristics of your older rock. You will have your metamorphic rock. So you can see sedimentary rock, metamorphic rock, they're made in different way. Okay, this one metamorphic require heat and pressure, and this one require the compaction and cementation and deposition of your rock pieces. Okay, so we have 3 types of rock. You probably learned that from your high school already, but it's not based on the chemical composition. It's based on how the rock was made. The rock formation process. That is igneous, sedimentary, metamorphic. All right? Okay, so let me stop here. On Thursday, let's jump into the classification. Okay, the sub-classification of different type of rock. And you will know, oh, this rock, the history. 4.6 billion years history in this smaller rock. When you know this, guys, you will get crazy. You won't, be able to, stay quiet, stay, ignorant when you're in the mountains. You hear the story told by those rocks. That is amazing. All right, okay, so let me stop here. Let's see, stop share, stop recording.